Hi, this tutorial covers AND probability for independent events. Alright, so let's consider the following chance experiment. A jar is filled with 6 red marbles and 4 blue marbles. The marbles are mixed up and a marble is chosen without looking. Uh, the color is noted and the marble is replaced in the jar. The marbles are mixed again and a second marble is chosen. The color is noted. So we're going to let event A be the event that the first marble is blue, and let event B be that the second marble is blue. So first of all, are events A and B independent? Okay. So if we know that A occurs, does that affect the probability of B, the probability of getting a blue marble? Okay. And I would say no. Okay. The reason why is that there's a 6 out of 10 chance of getting a red, and a 4 out of 10 chance of getting a blue. Now, because we're we're sampling with replacement, the probabilities aren't going to change. So the probabilities will always be 6 out of 10 and 4 out of 10. Okay, so are the events independent? Yes. Okay, because we have replacement. Okay, so now let's consider the outcomes of this experiment by making a sample space. Okay, now we're going to make the sample space a little bit different. So what I'm going to do is I'm going to make just kind of a square here. So for the square, we're going to put the outcomes of the first draw along that side, and we're going to put the outcomes of the second draw over here. Okay, so the way we're going to split this up is with the first draw, we knew that there was a 60% chance of getting a red and a 40% chance of getting a blue. Okay, so we're going to put red here, and I'm going to put 0.6. Okay, so what we're going to do is try to split it so it's about 60% of the of this square. So we'll move it over a little bit past midway. So that's going to be about 60% there. Okay, so then the rest of my outcome here would then be blue. So blue would be 0.4. Okay, now again, these are independent events. So what I'm going to look at now is I'm going to do this kind of the same breakdown. So for draw 2, I still have a 60% chance of a red, 40% chance of a blue. So I'm going to split this up again so that it's at about 60. It's about a 60-40 split. So about like so. So now this is red at 0.6, and this is blue at 0.4. Okay, now this whole side represents a probability of 1. This whole side represents a probability of 1. Now, if we're thinking about area as probability, 1 times 1 is 1. So the probability of all of these outcomes added together will be 1. Okay, if we use that same idea to think about this outcome, getting a red on the first and a red on a second, if we multiply those together, that would be 0.36, okay, which is 0.6 times 0.6. Okay, if we do a blue first and then a red second, it'd be 0.4 times 0.6, which would be 0.24. So it would be 0.4 times 0.6. Okay, down here, a red first and then a blue. That probability is the same as a blue then a red. I'll just write it as 0.6 times 0.4. Okay, and then a blue and a blue is 0.16. So 0.4 times 0.4. Okay, and we can see that these 4 probabilities will add to 1. Okay, 0.24 and 0.26 add up to 0.4. 0.36 times 0.36 plus 0.24 add up to 0.6. So altogether these will end up being 1. Okay, so the main idea there is that we were multiplying. Okay, so what that was an example of is, and a little bit of motivation is for what's called the special multiplication rule. So if events A and B are independent, like they were, the probability of A and B equals the probability of A times the probability of B. Okay, so remember that event A was that the first marble was blue, so probability of A was 0.4. and the probability of B is the probability that the second marble is blue. Well, that's also 0.4. So then to find the probability of A and B, you simply multiply these two together. So the probability of getting two blues, A and B, was simply 0.16. Okay, so just using that special multiplication rule. Now, we call it a special multiplication rule because it's specific. It's specific to the conditions where A and B are independent. Okay, this won't work as well if we're dealing with, or this won't work at all if we're dealing with dependent events. Okay, so now if we think about this example, a die is rolled and the value is noted. The die is rolled again and the value is noted. So we're going to let event A be that the first roll shows an odd number. Event B is that the second roll shows a 1 or a 2. Okay, so to use the special multiplication rule, let's first of all decide if A and B are independent. Okay, if we're dealing with the first roll and the second roll, okay, will the second roll be affected by the outcome of the first roll? And no. Okay, when you roll a die, the outcome from the first has no bearing on what the second die roll. So A and B are considered independent. So we can use the multiplication rule, but in order to use the multiplication rule, we need the probability of A and the probability of B. So the probability of A shows an odd number. So there are 6 possible rolls on a die. 3 of them are odd. So this will end up being 3 out of 6. So the probability of A is 3 out of 6. Shows a 1 or a 2. So again, there's 6 possibilities. 1 or a 2 counts for 2 of them. So this would be 2 out of 6. Okay, so the probability of A and B, since A and B are independent, would be the probability of A times the probability of B, which is 3 out of 30, or 3 sixths times 2 sixths. 3 times 2 is 6. 6 times 6 is 36. So there would be a 6 out of 36 probability. And if we want that as a decimal, we could take 6 divided by 36 and get about 0.167. Okay, so this is approximately equal to 0.167. Okay, so that would be the probability of rolling an odd number on the first roll and a 1 or a 2 on the second roll. All right, so that has been the your tutorial on and probability for independent events. Thanks for watching.